So if you remember the keynote with Francis, he had the Palm API extension, and he asked what sessions are worth viewing at F3, and this session was on the list. So based on that, no pressure. So who am I? Question I ask myself every morning. So my name is Jason Berryman. I'm a freelance Google Cloud architect and a Firebase consultant. As mentioned, I'm also a Google developer expert for Firebase and Google Cloud. I work predominantly with a mixture of startups and also on some enterprise transformation projects, helping people either take legacy applications and make them into something serverless, or somebody building a new application that wants to use serverless technologies. And typically for that, we're using Google Cloud Platform and Firebase. So what are we talking about in this session? We are going to ask why NoSQL and why not. Some typical design errors and patterns that developers make when they're building applications. We'll then look at how to get your user experience or UI designs and use those to build your data model in Firestore. Then we'll take a little bit of a switch and do a deep dive into Google Cloud Platform and how you can extend your application. So you built a Firebase app, you want to add more functionality, we can look at extending your app using GCP. And any lawyers in the room? No, we're a little bit on data governance and why data governance is important in this day and age for your application, particularly when you're handling consumer data. And then if we've got time, I'll put Q&A, but potentially we might not have time for Q&A, but you can come and find me afterwards. So why NoSQL? So NoSQL databases are designed to be very fast and efficient. They're really there to provide read optimization. So you might write a single record to a database, and that record might be read thousands, tens of thousands, maybe even millions of times. So having a heavyweight relational database server serving all of that and having to do joins each time is both costly and adds additional latency. So by using NoSQL databases, we can drastically reduce the latency, we can reduce the cost, and it also gives us a flexible data model. So Firestore is designed to scale to the size of the result set, not the size of the data set. So it's a fantastic use case where you've got maybe millions of records in a database. And let's say, for example, we get hungry and we say, let's find the top 10 pizza restaurants in Prague. And Firestore will just say, here you go. It's already indexed, already ready. Let's say we add in lots more pizza restaurants. Let's say we add in lots more users. Firestore can scale. So it scales horizontally. Most relational databases scale vertically. So this gives us the ability to build an app with pretty much zero maintenance. So a quick look at some typical design errors that I see when I'm working with clients building applications using Firebase. So firstly, treating Firestore like they would a relational database. So they are doing multiple lookups. They're maybe creating separate collections as though they're tables and storing data individually. And these additional lookups start to introduce latency and cost. So here you can see we've got an order application. So we're actually ordering pizza. The theme of today is pizza, you'll notice. I like pizza. By the way, any potential clients in the room, I work for money or pizza. So we've got our application, and you can see we've got 3 tables in a typical relational database structure. We've got our order table that has a user ID and a restaurant ID. And then you can see we've got a restaurant table and a user table. So in Firestore, if we wanted to fetch that data, we would need to fetch the top one, then we'd need to go and fetch the other 2. So using a NoSQL model, you can see here what we've done is we've combined all of that data into a single document. So that's one fetch, one read, very fast, very cheap. The other typical error I see is people collecting all of their data at startup and then storing it in something like SQLite or in some local cache. Now, there are some applications where that's required. Maybe you need some kind of offline handling and filtering and searching that you can't get from the standard offline mode that Firestore serves. But typically, you'll have issues with scaling because you're trying to store all of that data on your client. You're also going to have a few... I can't actually read what I've put down here. Let me go over here and see what my second point was. Yeah, so real-time updates. So real-time updates, if you're using real-time push on snapshot event listeners in Firestore, that's harder to deal with if you're storing your database locally. And lastly, it makes your client much more complex. So you're putting a lot of work into the client, particularly if you are building separate clients for iOS, Android, and web, because for some crazy reason you're not a Flutter developer, then you've got 3 versions of your app that have all got to manage searching and filtering consistently. So typically, when I'm starting with a project, I start with the user experience and the UI. So first thing I do is take all of the fields on a single page and put those into a document, because that way I know when I'm serving that page, I'm only serving and fetching a single document from Firebase. The collections and sub-collections typically follow the user journey. So the first page you come to has a document with some fields. The next page you drill down to is then a sub-collection, and so on. You'll see that in some examples. And finally, I separate data into different roles. And again, you'll see why. We'll cover that later, where we look at roles and user roles and why it's important to separate that. So here you can see we've got our pizza application, or we've got a menu application for a restaurant. And in here, we've got our pizza. And we've got all of the data from the pizza that's on this page stored into a single document. In Firestore, we have this concept of collections and sub-collections. So hopefully most of you will be familiar with Firebase and will have used this functionality, but it gives you the ability to take a single document and create a sub-collection of that document and further sub-collections of that. And you'll see why that becomes useful. So here we have our restaurant application. We're going to take some orders. So our restaurants, they have a listing, and then we can actually click on an individual restaurant and we can see the data for that restaurant. So that typically will be in our restaurants collection. As a sub-collection of our restaurant document, we're then going to add an orders sub-collection. And that will list all of the orders and show the order page for each of those orders for the restaurant. And then again, we can drill down to a second sub-collection where we are then able to view the items that are on that particular order. And you can see our order contains a whole load of information, including the user ID and the username, the restaurant ID and the restaurant name. So we've denormalized that information and put it into that single document. So we're not having to go and fetch multiple documents in order to fulfill any of the pages within our app. So where do we actually put these sub-collections? So our orders could be a sub-collection of a restaurant document. They could be a sub-collection of a user document, or they could just exist on their own. We've got some flexibility within Firestore to handle all 3 of those cases. So let's take a look at one of them. So here you can see we've used the order collection and made it a sub-collection of a restaurant. And then order items is a sub-collection of that. If our users want to view the orders that they've created, then we can use what's called a collection group query. And you can see in the collection group query, we can simply find anything in the orders collection which matches the user ID. Now, this is great until you notice at the bottom we've now decided we want to add in 3 further fields into our database. And these are cost fields. We don't want to share these with our users. Only the restaurant managers want to see this information. So how are we going to deal with that? I've noticed I'm pointing this at the screen over there, and actually I should be pointing at the computer. So what we're doing here is we're taking our order information and we're splitting the data the restaurant uses into role-specific collection. And so here I've got within my orders, for the user, I'm fetching the information for the orders that they've got, but they can't see that cost information because it's actually in a role-specific document. Let me go back. There we go. So here for the restaurant, they've got their application. They can see here's a list of all the orders on the system, and they want to look at the order for table 14. So when they drill down into table 14, they can then see the cost and the sales information, because you can see here from our top document, we've got the information that's available to everyone. And then in the bottom, we've got just the fields that we want to show for the restaurant. And these exist in our role-specific collection. But maybe the restaurants want to see a list. Maybe they want to see the cost price alongside the sales price. Now, in order to do that with our previous model, we would have to fetch the collection of orders, and then we'd have to go and fetch each role-specific document individually in order to display that. And as we discussed earlier, we don't want to do that because it introduces latency and cost. So the answer is denormalize. So let's see how it looks once we've denormalized. So here you can now see we've got 2 versions of the same document. We've got the version that the user sees, and that's a sub-collection of the user document. And we've got a version that the restaurant sees, which is a sub-collection of the restaurant document. And typically, we would use something like Cloud Functions, where when an order is created by a user, we will trigger a Cloud Function to create that document within the restaurant sub-collection. And then we can go and query a separate database, separate collection somewhere else, and find the cost price. And then the final thing I want to cover, looking at how we actually model our application, is counts. And I've added this because yesterday in the AMA with Puff, somebody asked about counts and the cost of counts. So counts, if you weren't there yesterday, counts are charged at 1 document read per 1,000 index counts. And for most applications, that's not going to be an issue. But if you've got an application where maybe you've got thousands, tens of thousands, millions of documents, you don't want to be counting millions of documents to come back with a result. So let's say, for example, I've got notifications on my screen. Maybe I've got 107 unread emails. Maybe I've got 109 unread emails. I really don't care about that personally, as long as I know that there's quite a few emails to go through. Maybe because I've been away on a trip to Prague, for example. So what I do is limit the count to 100 documents. And then in the UI, you can see here we're showing 1 to 25 of our 74 documents returned. And then, if we hit 100 in the UI, we can simply display 99 plus, or many, or whatever word you choose. So engaging with the UX UI designers at the stage to say, do you actually need to know exactly how many are there? this may save you a lot of cost and complication by just saying there's loads of them. So next thing I want to look at is how we can extend with Google Cloud, because Firebase is a fantastic product and it's very concentrated to do certain tasks extremely well, but it doesn't do everything. So there's reasons why you want to use NoSQL. We've seen that it's a really quick, powerful way to serve our UI, serve our mobile applications. Sometimes maybe we need a relational database. So we want something that can do some aggregations, some quick, powerful reporting, some stuff that maybe we haven't built indexes for in Firestore, because this is new information that we're querying in a way that we don't typically query within our app. And then finally, search. So you may have seen when we looked at extensions in some of the sessions that there are search plugins for Algolia, TypeSense, and a few others. Search has some, again, very specific things to do with filtering, facet counts, other things that fall outside the realm of Firestore. So Firebase has a few options. And the slide theme has changed. We're now on my slides for my talk at Next, because it was easier for me to copy and paste them in. So we've got a few options within Firebase. We've got the real-time database, Firestore, and cloud storage. Why do we need relational databases? Well, as we've discussed, sometimes you just need to do that little bit extra that you can't do in Firestore. You need to do some dynamic querying. And so we've got a few options within Google Cloud. If you're building an app that's going to scale to millions and millions of rows of information, then Cloud Spanner is a fantastic resource for doing that. It's expensive, but it's extremely versatile in what it does. So one of our other options is AlloyDB. And AlloyDB recently at Cloud Next announced a new AI version where you can actually start to do AI with AlloyDB as well. And effectively, this is a managed Postgres database in the cloud. And then finally, if you really want to get your hands dirty, you can go with Cloud SQL. Now, Cloud SQL is a managed database, so there'll be a certain element of IOPS. And the nice thing about Firebase is you enable Firebase on a project, and it's pretty much hands-off from an IOPS point of view. Cloud SQL, you will need to do a certain amount of management of your database service in the back end. Search, as I mentioned before, we've got Algolia and TypeSense are both available as Firebase extensions. There are some others. There's support for Elasticsearch and MeliSearch. The nice thing about these two is that you can call them directly from the client. So you're looking at SDKs that provide you similar functionality to Firebase. So we've designed our application. We need to know what resources we're going to use for our application. And this is where we can look at polyglot persistence modeling, because typically one data store isn't going to be enough. So you can see here I've divided our operational data store into the real-time database, because maybe we've got a user canvas and we're tracking pointers and lots of rapid stuff that's happening. We're using Cloud Firestore because we need to store our main documents. So for example, of our restaurants, we're tracking orders, menu items. All of these things can go into Cloud Firestore. Cloud storage, we're putting our images. So our nice image of a pizza would go in cloud storage. Algolia, as we discussed, we're going to use for search. Then if we come across to the GCP side, we can see we've added in AlloyDB, and that's going to be handling our reporting. Now, somebody decided we want some IoT devices. Every pizza oven, every fridge that has a temperature monitor and sensor on it, we're going to start adding and collecting this data. So we know that in a restaurant somewhere in the world, if the temperature in a fridge falls too low, or a component in an oven, for example, starts to fail, we can actually capture that. So we've added in Bigtable and Cloud Memory Store, and these will allow us to cache some of the data to do with the sensors, and then store that sensor data in Bigtable as a time series database. So we can then fetch that really quickly and start to do some powerful reporting on time series. And then finally, we're going to add BigQuery into the mix. And this gives us some really deep analytics about our app. So our customer can go in, they can view the application, they can see how the users are processing, they can see how the IoT devices are managing, they can see how many orders are going through the system. And then they can attach something like Looker Studio or Looker to BigQuery and start to produce some of those statistics. So we've looked at all of these options. Now somehow we've got to get our data from Firebase into our Google Cloud products. So for Firestore, real-time database and cloud storage, it's really simple. Firebase have given us a set of excellent SDKs, so we've got Flutter that we can use, and we can talk directly to the databases from our Flutter app. When it comes to search, Algolia, again, they've got a fantastic client SDK. Now, typically, when you're using the SDK, you might have public access to that data, so that somebody, for example, can search a menu within a restaurant. But maybe they don't want to search public data, they want to look at their orders, or a restaurant wants to look at orders. And so Algolia gives you the ability to create a token which has a built-in filter. And we can fetch that token using a callable function. Callable functions, if you're not familiar with them, they are like a Google Cloud function, or a cloud function for Firebase, but they have the Firebase authentication built in. So they will provide the user ID to your function, which you can then use to go and create a JOT or a JavaScript web token from Algolia, and that will include a filter to say only show orders for this user ID, or only show stuff for this particular restaurant ID. When it comes to talking to some of our database products, we can use callable functions, again, to query our Cloud SQL database or Cloud Spanner. And then, as we start to add data into the system, we want to push it through to our backend. So we already saw extensions. Extensions are great for putting data into Algolia and BigQuery. We can also use Cloud Functions. So Cloud Functions can be used to create custom functions to push our data into AlloyDB. You see I've added BigQuery. Again, why do we need a function for BigQuery? We've already got an extension. And I'll show you the reason for that in a few minutes. And then finally, if you're streaming lots of information into a lot of back-end services, maybe you want to use something like Cloud Workflows or PubSub. And in this situation, we can take our information that comes through Cloud Functions, push it into a PubSub topic, and then from there we can feed that through into other services in the back end in Google Cloud. And the nice thing about PubSub is it works cross-project. So if you want to put all of your analytics data in a separate project to your main operational data store, PubSub is a great way to do that. So we've looked at how we're actually going to create our application, how we're going to serve the UI from Firebase, which data source we should use, and how we can use polyglot persistence modeling to stitch all of this together to make an application. Now, I did mention data governance, and I can tell you're all really excited for data governance and compliance. But there are some important messages in here which, if you're an app builder, there's a few things which, if you take into consideration, could save you a lot of time and cost in the future. So the first one is classification. I've got an example coming up in a minute where we'll look at classification and how we actually store the data and classify it to make sure we're not storing personally identifiable information in a way that could become a problem in the future. With legislation like GDPR, and in other countries they're introducing similar things, maybe we need to look at data sovereignty. even. That's a difficult word to say when you're standing on stage. Let me have a drink of water. So Firestore this year released a feature where you can actually specify multiple Firestore databases for a project, for a single project, and you can choose where to locate them. So by putting all of your European users into a European Firestore database, and you can put all of your US clients into a US database, and the same for APAC, you can divide up your users so that their data is stored regional to where they are. That gives us two things. That gives us a tick in the box that we've made some efforts at compliance to make sure our user data complies with things like GDPR, but it also brings the data closer to the user and reduces latency. And then finally, retention. You might find that some of our users, their data, we're only allowed to store it for, let's say, 6 years. So data retention policies can help with that. So here we're looking at classification and archiving, and you can see we've got an extension that's writing data into BigQuery. And typically the Firestore, or the Firebase extension for that, you can see it writes the data as a single JSON string. Now that's great, but maybe you don't want to write all of the information that's in your Firestore database into BigQuery. So this is where we can take a cloud function. And you can see in the cloud function what I've done is, instead of writing a JSON string, I've written individual fields into a table, and I've chosen which fields I want to write and which ones to exclude. Now let's take another example, and here I've got some data including a notes column. Can anybody see any reason why I might not want to write this data into BigQuery? Yes, so credit card numbers. So here I've got quite a lot of PII, personally identifiable information in here. I've got a name, I've got an email address, and I've got a credit card number. Now, things like the name and the email address, I can actually deal with. I can say, I don't want to write those to BigQuery, so I don't include them in the payload that I'm writing into BigQuery. But the notes field, there's stuff in the notes field that I would really like to store and archive, but I don't know how to find out what is PII and what is stuff that I can safely store. So this is where we can add in a service called data loss prevention. And DLP, I would recommend anywhere that you're archiving notes field, any free text fields, pass it through DLP, because it will give you the ability to redact things like card numbers, things that users do that you wouldn't expect them to. Now, with regards to the name and email address, maybe we do want to store them because we want to use them later, but we don't want everybody to see them. So we can use column level security in BigQuery, and we can actually stop certain users from being able to see that information. We can also use hashing, so we can hash the information so it's available to everybody, but unless you've got a key to unlock it, you can't actually view it. And then finally, a little bit about lifecycle management. So in our application, maybe we've uploaded some photos. The photos that are being shared with people, maybe for the first 90 days, we want everyone to have free and easy access to them. After 90 days, they start to get a bit stale. People view them less. So what we can do as app developers is we can move them into nearline or cold line storage, or even into archive storage, and that makes it cheaper for us to store that data. We can still fetch it. We pay a little bit more to fetch it. So the idea is that a user, let's say for example, after 90 days, you can set your own time limits, won't be fetching that photo quite so often. So you don't mind paying a little extra for them to fetch it, but you're saving a lot of money in storage. And then at some point you can set a retention policy that can delete it completely. And the same with BigQuery. If you've got data that you're required to only retain for a number of years, 10 years for example, and again GDPR has got a lot of things in to do with how long you can store a user's data, then these retention policies are things that you can build in to both GCS and BigQuery. And that's it. That's everything from me. I was going to do Q&A, but I think probably out of time for that. I will be around if people want to chat to me. My details are here. I do have a YouTube channel, Backfire Dev, so please subscribe. And if you're watching this on YouTube later, please hit the like button. Fantastic. Thank you very much.